Let's look at integral calculus. And the Fundamental Theorem of Calculus. So, quick recap on differential calculus. Differential calculus lets us find the slope of a function at a particular point. How does it do it? And our slope, f dash at x, is equal to the limit as delta tends to 0 of that thing. So we can differentiate f of x into f dash of x by this process, and geometrically we're getting the slope of this tangent line. Question is there an anti-differentiation we can do, so as to find something that differentiates to f of x? Well, we know, for example, that x to the k over k factorial differentiates to x to the k minus 1 over k minus 1 factorial. So obviously x to the k plus 1 over k plus 1 factorial is going to be an antiderivative. It's going to differentiate to x to the k over k factorial. But can we find some geometric understanding of this antiderivative? It turns out we can. If we consider the area function, area at x, here's x, and this is area for that x value. So the area from 0 to x of the function. Then this area function is our antiderivative, i.e. if we differentiate our area of x, we get f of x. Now this isn't actually that surprising. If you look at a discrete example with squared paper, so for example, at this point the value of the function is 2 and we're gaining 2 squares. So the area is changing by plus 2. At this point here, the value of the function is 3 and the area is gaining 3. It's changing by plus 3. Here the value of the function is minus 1. The area is changing by minus 1. So the rate at which the area is changing is the value of the function at that point. This is not meant to be precise. This is an intuitive way of squaring it. So let's be a little more precise. Now let's look at a continuous function. Here's our delta. So by differential calculus, a dash of x equals the limit as delta tends to 0 of a x plus delta, which is just this big area, minus a of x, which is just this smaller area, that's a of x, right? And that big one's a of x plus delta over delta. And the difference between these two areas is just this shaded region, which can be separated out as this rectangle plus this triangle. So that's the limit as delta tends to 0 of the rectangle plus the triangle over delta. And what is the area of this rectangle? Well, this value there, that's just f of x, isn't it? This height is f of x. So that's just f of x times delta, width times height. Which is just the limit as delta tends to 0 of f of x plus triangle over delta. And as delta shrinks to 0, this contribution becomes negligible, so this disappears. And we're just left with f of x. Maybe that was a bit long-winded. Maybe we should have just said this difference in these areas is approximately equal to the area of that rectangle. Therefore, that over delta is approximately equal to f of x, and as delta shrinks to 0, that approximation gets better and better. Okay, it's still not entirely rigorous because we've assumed this contribution from this triangle dwindles to 0, but we haven't proved that's the case. So how do we go the extra mile and do this formally? Well, we'll need to make use of the fact that our f is a continuous function. So if you haven't watched the video on continuity, I recommend you do that at this point. Otherwise the following may not make sense. Okay, so recap. What's a continuous function? So f is continuous at x if and only if for any epsilon band we make around f of x, we can find some delta band mapping to within that epsilon band. So no need to make it as big as possible. Just there we go. So this is our delta. So this is our epsilon band around f of x, and this is our delta band around x. We know that within this box f is entering one side, leaving the other side. It's never going over the top or under the bottom. F is within that box, over that interval. So what can we say about this area here? Well, it has to be somewhere between this area, which is f of x minus epsilon in height, and delta across. So this shaded area is somewhere between delta times f of x minus epsilon and this big rectangle, which is that's f of x plus epsilon plus epsilon. So delta f of x plus epsilon. And this is a of x plus delta minus a of x, just like we had here. Okay, so now we know that we can just divide everything through by delta. So that must be between f of x minus epsilon and f of x plus epsilon. And it doesn't matter how much you shrink delta, this is always going to be true. So you can take the limit as delta tends to 0 of this thing, which doesn't depend on delta, so it's just the same, equals the limit as delta tends to 0 of this thing, which is what we're after. This is our a dash x. Yeah. To get from this step to this step, we're just taking the limit as delta approaches 0. So the distance between f of x and a dash of x is less than epsilon. I don't know if this last line makes it any clearer for you. You could use either of these two, same deal. But the gist is that it doesn't matter what we set epsilon, this is always going to be true. So, right at the beginning, we set our epsilon band, then we created the delta band, and we showed that this area lies between that and that. So we showed that a dash of x lies between that and that. And we showed that the difference between f of x and a dash of x is at most that epsilon we started with. But now we can just shrink that epsilon down to 0 and it's always going to be true. So this is true for all epsilon greater than 0. Therefore, these two things must be equal because the distance between them is smaller than any positive number. So f of x is equal to a dash of x. Done. And that is the fundamental theorem of calculus. Now suppose you have a function and you want to find the area between 2 points, A and B. So this area is just going to be area for B minus area for A, isn't it? And we can write this as the integral of f of x with respect to x. You need that if you're using more than one variable, like if you have a 3D function where you've got x and y and z, and z is a function of x and y. You can differentiate and integrate along one direction. Anyway, don't worry too much about it for now. So we integrate from a to b. If you see this expression, that's the picture you should have in your head. You're finding that area between x equals a and x equals b, the area under that function between x equals a and x equals b. Notice as well, area can be negative. So here's a sine wave, for example, over a single period. The area is equal to 0 because the negative area cancels with the positive area. They're equal. Now, one thing to be careful of is, suppose we've got a parabola, and then we've got the same parabola but just higher up, and then the same parabola but higher up again. Now, can you see that at a particular point, at a particular x, the slope on all three parabolas is going to be the same? So our f1, f2 and f3, all of them differentiate to the same f dash of x. So if that was x squared plus 1, x squared plus 2, they all differentiate to 2x. So if you ask, what is the antiderivative of 2x? Well, 2x can integrate to any of those and more. A whole family of curves, in fact, x squared plus any constant, because a constant term differentiates to 0. So every time you integrate something, you're actually creating a family of curves, all of which have the same slope at a given point. They're just shifted up and down. And this is known as the arbitrary constant of integration. So if you take a function and you integrate it, then you get, let's call it big F of x plus our arbitrary constant of integration, and we differentiate it again back into f of x. That's okay, but if you were to go the other way and take your f of x and first differentiate it and get f dash of x, and now you integrate it. I'm stopping short here because we don't really complete the cycle here. Now we've got f of x plus k. A final note on this integration sign, this integral sign rather, it does look like a big S, and that's not a coincidence. It's a it can be thought of as summing thin slices. So here's our function, and each of these has a width of delta x, and we are summing f of xi. This is x0, this is x1, this is x2, da da da. So f of xi times the width. And now we're taking the limit as delta x tends to 0. So you can imagine this becoming a more and more fine-grained approximation of lots of little rectangles. Finally, let's give a quick worked example. So calculate the area underneath y equals x squared from 0 to 1. So we need to integrate x squared from 0 to 1 with respect to x. Well, x cubed differentiates to x squared, and bring the 3 down, 3x squared. So therefore x cubed over 3 is going to differentiate to x squared. Therefore x squared is going to integrate to x cubed over 3. So we're looking at x cubed over 3. That's our a of x. And now we're just looking at a of 1 minus a of 0, which is 1 cubed over 3, a third minus 0, so 1/3. So we could say this is our theorem, Fundamental Theorem of Calculus. This is our sketch proof. This was another sketch proof, so sketch proofs 1 and 2. And this is our formal proof. And then here we were introducing integral notation. Okay, done.